Okay. Okay, so then we officially start, okay, the study of section 1. So section 1 is for you to gain the basic understanding about the robotics. Okay, just now I mentioned for our student, they will spend 1 semester to study robotics course, right? Then good news to you is you just going to spend a half day to know like the major knowledge concept behind robotics. Okay, but another good news to you is actually the other topics which are related to robotics will be covered in section 2 and the remaining section, because you can, from a knowledge point of view, you can relate all these 3 major topics together. That is why we are pretty something very interesting for you to know. We managed to combine these 3 topics together, right? Then at the higher level, you could consider inside the robot, you have a mini version of IoT. Understand? Then if you treat a robot as a single device, actually a robot could be considered as a mega actuator. Regardless complexity of a robot, just think a robot is just an actuator. Or you can also think a robot as a sensor. You try to gain this extra view or unique view, then you will feel totally real, right? So, and this will make you feel excited about the study of this course, okay, which cover robotics automation and IoT. Okay, so for today's session, I'm going to give you or help you to understand answer to these 3 questions. What is a robot? What are the motion system, or what is the nature of the motion system inside the robot, right? Then why a robot is able to perform a task, right? Or how to impose the task into motion. So these are the 3 major questions. As long as you understand the answer to these 3 questions, then it should be good enough, right? And in future, if you want to know more about robotics, then once you go back to your university, then you can choose robotics course, right? So at least today, we are helping you to build up a solid foundation about the study of robotics. Okay, first answer you need to know is the answer to this question: what is a robot, right? So, and before we jump into the answer to this question, okay, this slide help you to understand, okay, what will be learned by our student when they spend 1 semester. So you see, you have 4 major modules, right? And inside each module, you have an individual lecture. So this will be the topics learned by our student within 1 semester. But since here we cannot ask you to stay here for 1 or 2 years, right? So then I try to help you to understand all these major topics within half day. Okay, so for this first lecture in session 1, so we will quickly go through the definition of the robot, history of the robot, what can be done by robot, and the major topics of which I'm related. Okay, so then if you want to know what is a robot, okay, from this slide, then you will see, okay, we have 3 examples of a robot which looks like a human being, and also you see a dog-like robot, right? Then if you want to know, okay, what is the exact definition of a robot, okay? And here you may also want to know how come in the media so many people are interested in robotics, okay? The major motivation is because robot could help us to do a lot of tasks in industry, right? So this is why a lot of interest about robotics. Okay, and before we look at the detail of answer, you will see here you have 3 examples which looks like a human being. then automatically, okay, but the good news to you is a translation of a robot in Chinese means what? In Chinese, robot means what? 机器人is, but it means it's a mechanical man, right? So, but in English, it's not related to a human being, right? So then automatically you will think about, okay, the similarity between robot and the human being. But this slide is very philosophical. Okay, I may not give you the answer, but at least challenge you about thinking to this two question, right? So if you look at this tree, and the mainstream thinking is about the relationship among all the animal and the human being, and the mainstream belief is about the evolution, bottom-up evolution, right? But the thing is, once you in future, for those of you in future, you are going to do research in robotics. I guess 10 or 20 years later, you will more or less change your mind, right? So are we the result of a bottom-up evolution, or are we the outcome of a top-down design? I guess 20 years later, you will believe that we should be the outcome of a top-down design. So pay attention to this keyword, design, right? Okay, so this is just for you to think through. This is a very philosophical question, all right? And today, a lot of people more or less will jump to this answer, right? Okay, so then what should be the definition of robot based on the previous one of the animation of the slide? Okay, so these are the three major items or information inside the definition of the robot. The first two could equally apply to industrial robot, but the last one is very important, right? So in the old day, we just focus on first two information. That means the robot is a machine which could execute motion, or robot is a machine which could perform a task through execution of the motion. That's very simple. But in today's context, we need the robot to be able to interact with the people. Reason is we want the robot to work together with the human being, right? And in particular, we want the interaction to be occur at the cognitive level. So pay attention. We can interact with the machine at the signal level, right? We issue the signal, then robot responds to the signal. But however, in today's context, we want the robot to speak our language, right? And today, many of you heard of ChatGPT. And what is ChatGPT? Basically, is to enable a machine to communicate with a human being through the use of a language, right? And this diagram drawn by us in the year 2008. You see, 15 years ago, we already started to work on the human-robot interaction at the cognitive level, right? Okay, so that's about the definition of the robot. So at least by now you know that robot is a machine which could execute motion, could perform a task. In particular, you may say robot is a machine with a certain level of intelligence which enable them to communicate with the human being, right? So now you know what is robot. Then it's very important for you to know, okay, what motivates human being to invent robot, right? Why to create a machine which looks like a human being or which have a human-like intelligence, right? So this is very interesting. Why the history of robotics is very important? The reason is if you consider teleoperated robot, you see in the textbook, okay, when we talk about the family member of a robot, and this is inside, this is teleoperated robot. If we believe this guy is a member of a robot family, then how about PE, shuttle PE, right? Because this is the first generation of a teleoperated robot is right? PE is teleoperated robot. Then in this sense, then you will see the modern history of the robot actually was started in China, yes or no? And nobody mentioned that, even in textbook. So then you should feel proud of it, right? So now you remember, people, right? PE or shuttle puppet, okay, should be the first generation of a teleoperated robot. Then, but however, okay, the major contribution to modern history of robotics come from a Western country. Also, our ancestor initiated okay, the creation of robotics industry with the PE, right? Okay, because PE is a commercial product, right? So you can treat as a product with a commercial value, because when you show this PE, you will get paid, right? People will buy the tickets, right? So you can say that should be the first, the start of robotics industry, okay? But however, major history or major contribution of the robotic history comes from Western country. For example, invention of terminology of the robot, terminology of robotics, and at least the people say okay, the birth of the first robotics company come from the USA. And in the textbook, they mention this first robot, okay, robotic product in the history, but actually it's not. This is the second generation of teleoperated robot. All right, okay. So this just for you to know. And but you see how come the major contribution to modern history of robotics did not come from China. You can start to think about. Also, we have this. If let's say we continue this tradition, develop robotics all the way until today, then the history of robotics must be rewritten, right? It should be different. But you can start to think how come we did not continue our original invention in robotics. But you see, in Asia, there is another country, our neighbor, right? So the neighbor of China, they continue the history of shuttle puppet, right? Right? So we have a lot of interest in this animated machine. Then also we invest a lot. You see today, one of the most advanced robots is Azimo. This robot was developed by car maker Honda, you see, right? So this just help you to know. This is the history of robotic development by a single company in Japan, right? So then okay, we can start to see why it is not a Chinese company, okay? And this one has a video lah. Okay, sorry. So so this gives you an idea about the investment, the advance made by single company in Japan, right? So all these are right? And then here today, I guess this robot still occupy #1 position, right? And then today they are making many newcomer to the development of humanoid robot. So from this video, you can see today there are a lot of new startup company to do the development of humanoid robot. Actually, they are just trying to catch up with what has been achieved by Azimo, right? Yeah. Okay. So that's about the interesting history in robotics. At least if you can remember, shuttle puppet should be the first generation of teleoperated robot. Should be good enough, right? So shuttle puppet was invented in the 5th century, right? Now you may want to know how come there are so many interests in robotics. The answer is because of application. So there are a lot of application, right? So then you will see you can use robot to undertake a lot of industrial application, pick and play, right? Okay. So this is very simple. And then three robotic arms will work together, right? To undertake a very complicated motion, right? Okay. And then this is one more example. Okay, this is a typical scenario of making robot to help us to do dirty job. To do painting, this is very dirty environment, right? Okay. So this is a dirty job, and this is a difficult job, heavy, right? But they use this kind of robot to do pick and place of a heavy object, right? So if you ask a human being to do this task, then it should be quite difficult, right? Okay. And this is also a very difficult task. So you see the payload, the object frame, metal frame is heavy, right? So it's difficult for human being to undertake this kind of operation. Okay. And this one is dangerous to do welding, because welding is a dangerous task. Okay. So then we can use robot to do this dangerous task for us. Okay. And here is but due to time, I'm not going to play this full video. So this is the project undertaken by us. We have an industry in Fujian province in China to fully automate this process. Because in this workstation, the temperature is very high. You see the input material is a powder from. Then we increase the temperature to 200 degrees to melt the powder into liquid, then lower down the temperature, then liquid becomes solid, right? So this is a high temperature working environment. And because of the powder, then the quality of the air is no good, right? So it is not healthy environment for human operator. So this is why we have trouble to hire human worker. So then they want to know whether they can use a robot to fully automate this process. Okay. So you just see the bit of this is what we have done. Okay. China. So you see, this is the dual arm robot system. Okay. But this video at least give you some idea about the automation. So you see, robot is one of the major equipment for us to achieve industrial automation, right? So in the next session, we will study industrial automation. Then we will gain a little bit of knowledge about the similar process to this one. Okay. Okay, now this is the output from this process. Okay. So we move on. Then we have this video which highlight to you about the future trend in industry. I guess all of you know what is the name of this company. And okay, and you just need to pay attention inside the production line. You will see there is a lot of employment of robot. Okay. Now you see, okay. So three robots work together. I just play a little bit of video, so at least give you some idea about the importance of making use of a robot to undertake certain tasks in industry, right? Okay, it should be good enough because we may have other similar video. At least you see from this section, you see a lot of robot, right? There's no human being inside now. So you see this massive deployment of robots. And based on this scenario, you can start to think about the IoT. What do we mean by IoT? So in this scenario, you consider each robot is an actuator. They are interconnected together. Then this would be a typical example of IoT in industry. Clear, right? Think in that way, then we can relate these three topics together. Okay, so we move on. Then this is an application in the medical field. Okay, this also would be a very important application. Okay, for robotics. Okay, because okay, this is the example. You can say this should be the third generation of teleoperated robot. So you remember, shuttle puppet or PE should be the first generation of a teleoperated robot. Then in industry, teleoperated arm is the second generation. Then this is a medical robot. This should be the third generation of a teleoperated robot, right? So you see a real doctor, this is the real doctor, sit in front of a control station. Then through this control station, actually the doctor teleoperate robotic arm or medical robotic arm, okay? And then this robotic arm, actually you have four, okay? Enter the body of the patient. Then this is the inside the body. Then you see the robot arm doing this kind of operation. Okay, so this is a typical example of a third generation of teleoperated robot. Okay, so then again, when we ask this question, if our ancestor continue our tradition of inventing PE, right, all the way to medical application, then this should be the product invented in China. But actually, this is a product invented in USA, right? Okay, so that's about the application in the medical field. And in this area, this is a home service robot. I guess this application will create a huge production, right? Today, refrigerator is a standard item in every home or household, right? But in future, maybe service robot will be a standard item in every home. So then you see this is a huge market. This robot will create huge market, right? So this is the small demonstration which showing you that the robot is able to pick up a soft drink and deliver to a person in another room. Later on, you will see there's a person sitting in the next room. So you see, this robot is capable of autonomously undertake all these action or motion, right? And pick up the soft drink and deliver the soft drink to a person sitting in the next room. Okay, going now. And another impact from robotics is the transformation of today's automobile industry into robotics industry. And I guess many of you know the speculation about robot taxi or driverless car, autonomous car, or inside the video which present NTU, you see at least a few typical type of autonomous vehicle, right? This is the first generation of autonomous vehicle in NTU. This is what we have developed around the year 2000, almost more than 20 years ago, right? So this is a fully autonomous behavior. So at that time, we use this mobile platform, right? So we aim in robotic technology, then we can achieve this autonomous behavior, which is to follow a moving target. Okay, if the target in front stop there, then the car will also stop. So the task is to maintain a fixed distance, okay, between our vehicle and the vehicle in front. Okay, so I guess we may come back again to this kind of a video. So this is just a short demonstration. This video is quite long. Okay, so by this you know this is a demonstration made by us in year 2000, right? So this should be the first generation of autonomous vehicle like NTU, right? Okay. So, okay, so previous video basically highlight to you the major application of a robot in industry, in transportation, in the healthcare or medical field, etc. Right? Then you will want to know, okay, how to study robotics, how to apply the knowledge in robotics in order to guide the design of the robot, right? So you just need to follow this slide. This is the blueprint of any robot, right? So then you apply, learn the knowledge, okay, and to build up all these modules and link them together. Then you should be able to come out with design of your own robot, okay. But here we will cover the major topics. For example, in today's study, we will cover the major guideline for you to design robot's body and the major knowledge behind the equation of motion, right? How to translate tasks into motion, and then in particular, what should be the motion equation, right? Which allow your robot to perform the task, okay? And then for subsequent topics, actually for the knowledge about the control, you can apply the knowledge learned from the next section in automation to this special case. You can consider robot is also an automated equipment, right? So then you see you will learn knowledge about robot control. Then for the last two sections, you see, we will learn what is actuator, what is sensor, network with the sensor. Just like I mentioned, we can consider robot as IoT, okay, special IoT, right? So you have an actuator sensor inside, etc. Okay, and in order to design robot as a product, these are the guidelines for you to follow, right? So you must know who are the user, what are the needs of the user, then what should be the robot that you are going to offer to the user. Then what are the functionality of the robot? Then based on the functionality of the robot, then you can come up with specification of the robot. Then you just follow the design. Right? So this helps you to understand how to design a robot as a product. But for those of you with the mechanical engineering knowledge, then you can easily understand. If you do not have a knowledge about the design of the mechanical system, then you can learn. Okay, you can in the future you can subscribe to the course of design of the mechanical system. Okay, so that's about this first lecture, which help you to answer this question. What is a robot? So by now you know the robot basically the motion provider. The robot can perform a task. Robot can interact with people, right? And also you know that robot is very useful. All right. A robot has an interesting history which is related to the shuttle puppet or PE. Okay, invented in China, etc. Right? Okay, that should be good enough. Okay, so we continue, and later we make a short break. Right? Okay. So now we start the second lecture in today's session. Okay. So from the previous lecture, you know, robot is a motion provider. Immediately, you know that robot is a motion system. Okay, then you need to zoom into the detail about the motion system. Okay, so this slide just help you to understand that in order to fully understand robotics, you need to study all the lecture in detail, right? So today is just give you a short introduction, highlight to you the major topics, okay, which will help you to venture into more detailed study in future. Okay, for the second lecture, actually we cover here, we will be here, right? So we will go through, I guess, no, we are in here for the second lecture. Third lecture will be here, right? Tell you what should be the equation of motion. So now we highlight to you a little bit you see motion system here, right? So give you a little bit knowledge about the way how to design a robot's body. Okay, so then we must gain the knowledge about system, the robot is a system. Then this will be the key takeaway from this second lecture. What are the guidelines for you to do the design of the robots in different systems? Okay, so in order to design a robot as a product, so you must have a mindset of a system. Okay, so what is a system? Also, the definition is very simple, but it's extremely important. Because if you look at the whole universe actually is a system. So inside the system, you have a subsystem, right? So IoT is a system, automation is a system, robot is a system, right? So from now on, think in terms of a system, right? Then how to understand the detail of a system? Okay, this sentence is extremely useful and important, right? So you see, this is a recommendation from Nikola Tesla, right? He says that in order to understand the secret of the universe, or you can say in order to understand the secret of any system, just think in terms of energy, frequency, vibration. Okay, so here for the design of a robot system, pay attention to energy, right? Just now I mentioned robot is a motion provider. Robot can perform a motion. Okay, I guess all of you know that. Okay, what is a kinetic energy? What is the equation of a kinetic energy in physics? Is it 1/2 mv squared? Yes or no? How to compute kinetic energy? 1/2 mv squared. V is what? Velocity. So it means what? Motion comes from energy. So when you study robotics, think in terms of energy. Okay, so robot will transform, or robot is a machine which transforms energy into motion. That's it. Okay. When we study the second section, which is the automation, then you need to pay attention to this keyboard frequency, right? How to design control system. Actually, we need to design control system in frequency domain. Here you may ask this question, how come you never mentioned time? And then you may say, time is very important to us or not. Right? Today is afternoon, then today is today, tomorrow is tomorrow, then you have a time. But actually, you see, time is not important for us to understand the secret of the universe. It's not important at all, right? Okay, so, and interestingly, for those of you, if you have an interest in religion, Buddhism, right? So in Buddhism, we have another keyword, is a kong. What do we mean by kong, right? So actually, it's okay, ignore the time, right? So, and it's a sense of there's no time there. Okay, time is not important. Frequency is very important. Okay, so this just trigger you to singular. Okay, then 5 systems that you know. I guess this should be very easy. Education is a system, right? Economic is a system, right? So a car is a system, etc. Airplane is a system. It's very easier. Okay, so then for any system, your focus should be on these 3 things, right? What should be the input to the system? What should be the output from the system? What should be the relationship between input, output? Slowly, you will pay attention to this terminology because we will come back to this one. In second section, we study automation. Transfer function is means what? Relationship in frequency domain. Now you see frequency, right? So in frequency domain, we do not use this terminology of relationship. Relationship by default is a terminology in time domain. So relationship in frequency domain means a transfer function. That's it, right? Yeah, okay. So if you illustrate a system, then remember this diagram, right? A system has an input, has an output. We only pay attention to the relationship in frequency domain because that is more important. Okay. And in second section, you will know why jump into frequency domain. Because in frequency domain, we can visualize the signal flow of any system. That is unique. Okay, in time domain, you can never visualize a signal flow, right? So then you will see this is a good enough motivation for you to jump into frequency domain. All right, in frequency domain, you know the secret of any system, right? Because you can draw the signal flow diagram, okay, in frequency domain, right? Now, that is actually this is a mini version of a signal diagram. Try not to treat this one in time domain, otherwise you will lose the correct understanding. This is the typical example of a signal flow. You can only draw this diagram in frequency domain, right? Okay, and from here you see controller, system control sensor, and this is what feedback control loop. Okay, in the whole universe, almost all the system, basically all the dynamic system make use of this loop to achieve stability, right? Magic. This loop already tells you the very important secret in the whole universe already. Also, now appear very simple to you. All right, then you may ask, who is the first person to think about this feedback control loop? But this is a negative sign. Why negative? Why not positive? You see, this is a very important discovery, right? In engineering, in science, etc. Right? Okay. Then for the output of a system, regardless of complexity of the system, you only have two types of output: steady-state response, transient response. Okay. But this concept actually will also help you to study section 2 of automation, because we may come back to all these concepts. So this is the output from any system. So what we do mean by transient response? That means you look at the fixed output. Let's say this one, this is a fixed output. We call it a steady-state response, right? So you have the old steady-state response at 0. This is the new steady-state response. Then when the actual output go from all the steady-state response to the new steady-state response, you see sometimes we make a transition like that, sometimes we make a transition like that or like that, right? So all these transitions we call them as transient response, right? Okay, so we only have two types of response. Okay. Then how are we going to judge, okay, the performance of a system? Because the transient response is no good. Why this guy is no good? Because it's waste energy. It wastes our time, right? So we do not want to have a transient response. We waste our time, waste our energy. Because this is we call overshoot. Overshoot, we waste energy, right? Okay. So we need to define performance indicator to judge how good is the system. So this is a universal performance indicator, right? Okay, in order for you to remember all these concepts, the easiest way or simple guideline for you to remember these 4 numbers. 1, 2, 3, 4. 1 means what? We have one type of motion system, right? Here we deal with the motion system. One is one type of motion system. Two means two type of output, transient response, steady state response. Three means three key performance indicators. Three are here. Four means you have a four design method which allow you to achieve best performance, right? So these four you will know when you study section 2. Okay, you keep in mind this 1, 2, 3, 4. Then you can link all this together and feel comfortable, right? So just remember this 1, 2, 3, 4. One is one motion system. Robot is a motion provider. Robot is a motion system. Family. For two means two kind of output, transient response, steady state response. Three means three KPI, key performance indicator, right? Okay. Here is another question. Why I put this photo here? This is the president of Taiwan University, right? And the PhD from Stanford University. Then after retirement, he is doing a lot of study in religion, right? Because why I put it here, you pay attention, I guess you know this two Chinese keyword, 瞬间科技. But obviously, when he uses this terminology, it means he does not know control theory, right? In control theory, we do not use this term. We use what? We use a static system. Okay, here I help you to understand, help you to know this answer to this question. What are the best systems in the universe? Okay, it's easier to answer this question. Based on these three KPI, the best system must absolutely stable, yes or no? If a system is not stable, can it be the best system in the universe? Cannot, right? The best system must have a zero response time, zero waste of time. Yes or no? If you waste a lot of time, can you say this is the best system? No way, right? Response accuracy, best system must be 100% accurate, yes or no? Very simple. Then this kind of a system in engineering, we call them as a static system, 静态系统. Now you see, he uses 瞬间科技, right? So it means because he's doing study in physics, a PhD in physics, right? So he does not know engineering, right? So the best system in the whole universe are static systems. The majority of the systems in the whole universe are dynamic systems. These are the standard terminology, okay, about the study of a system, right? Then you see he does not know, okay, all this knowledge. Then he invent another terminology, but this is the misleading and confused people, all right? Okay, but he is trying to want to know in the whole universe, is there any planet in which majority systems are static systems or not? You understand the question? But for you, you know where is the Tianhang from? Right? So that means there must be a place where everything are the best in the whole universe. But actually, he found there is an answer somewhere there in the universe. Okay, looks like the majority system there are static system. Okay, this will help you to link the control theory or the theory of the system to the discovery observation about the universe. Okay, it's very, very interesting. Okay, then what do we mean by stability? You see, if a system go to infinity, this is not stable, right? So it go to infinity, not stable. But this is a magnetic stable means oscillator system. Okay, then response time means what? Let's say this is the old steady state response. This is new steady state response, right? If it takes time now, okay, to reach the new steady state response, then response time is not zero. Okay, for the best system, we want this time to be zero. Response accuracy means if let's say we want the new steady state value to be 1, but then this guy only reach 0.5, then you have error of 0.5. That is accuracy, not 100%. Okay, that is easier for you to know. Okay, So robot is a system, right? Just like I mentioned, is actually this is a control system. This is the blueprint of a robot. Immediately you know this is a system. Okay. So and this system has a many modules which are interconnected together. This is why now you see this keyword interconnected together. Means what? Just like I mentioned, robot is a mini version of IoT. Then immediately you know, right? Study of robotics actually contribute to the study of IoT because this is the mini version of IoT. Why? You see interconnect module. Okay, but they act together to achieve a common goal. Two major goals is what? Is to achieve a human-like skill or human-like intelligence. Right? Skill means what? Motion, right? To perform a motion. Intelligence means what? To think or to learn, etc. Right? Okay. So, and this is an example of a robot system for industrial tasks of doing welding, right? So then you see it's quite complicated, right? Okay. And this is for material handling. So you have a CNC machine, you have a conveyor. Then this robot arm is doing loading and unloading, right? So it's to handle the input-output material of automated machine. This is also for doing loading and unloading, yes or no, right? So you have a pallet. These are the you stack all the finished the output product, right? Stack them together. Then this is a conveyor. Then you have a robotic arm to pick and place. This is a system, right? Very easy. Another welding. You see now a full robotic arm. You see this robot has 3 eyes. You see the camera, and all these are the brand. Okay, you may ask, what is all these boxes here? These are the brand, right? Then you see how come robot brands separate from arm. Okay, because this is an industrial robot, but for humanoid robot, they all integrate together, right? Okay, yeah. And then robot system has an input, but you see, ideally, because you, if this is the first time for you to do the study of the robot, then you may ask this naive question: how come today's robot cannot understand task description? Okay, but you may think, how do we describe the task? Until today, description of the task are in the form of text, right? So today's robot have not yet reached that level of human intelligence, right? Which will enable robot to understand human language or the text, okay, written with the use of human language. And from here, you know, a lot of speculation on media are ChatGPT, robot is very intelligent, right? They can write a paper, write an article, etc., compose the image. All these are speculation, it's not true, right? But in Chinese, if you do the copy paste, you should not interpret this activity as creating something, designing something, right? To do the design, can you just do copy paste? You understand? 拼接并不是创作 right? 拼接知道吗 ？Okay, just copy paste, right? So copy paste has much to do with creativity, right? So it is a key to create the game, right? It's not much creativity there, right? Okay, so a lot of speculations at that level of copy paste has nothing to do with intelligence of creating something new, meaningfully new, right? Okay, this is why we must, human being must help robot to decompose the task into motion description. Then robot can translate the motion description into motion equation, right? So this is why until today, actually you can skip this step because this step is for us to help robot to do the understanding of task description or action description, right, etc. Okay, so this is why the third lecture I will start directly from here because this just for you to know today's robot has no capability to understand the meaning of a text written in a human language. That's it. This is why we still need to do a lot of research in AI. Okay, so obviously, then output directly from a robot is a motion, right? If the motion are related to the task, then the robot gives us the impression about the performance of the task, right? This is the illusion, understand? So strictly speaking, this robot is only able to perform a motion. If motion is related to the task, then we have this illusion about the performance of the task by robot. Actually, it's not. Robot does not know what is doing, right? Yeah. Okay. So then, based on this decomposition, immediately you know that what should be the major subsystem inside robot system. At least you must have a body to perform a motion. That means you must have a mechanical system which will physically enable robot to perform a motion, right? Then inside the mechanical system, they must have control system because all these motion are controllable motion, right? So then this is very important. Okay, first the robot must have a physical body. It's like a human being. We have a body, yes or no, right? So without the body, then it's like a condom, right? So all human beings has a physical body, a mechanical system. Then behind mechanical system, there is a control system because robot can do controllable motion, right? Then all the motion to be performed by robot must be programmable. Today, robot do welding, tomorrow robot will do transportation or material handling, etc. So these are the three major subsystems inside any robot, right? So these are the minimum version of a robot. But for advanced robot, you have a vision system, speech system, and communication system. Communication system means you communicate with the outside another robot. Internally, inside there you have an inner communication system, right? Okay. So these three are the minimum version of subsystem inside the robot. Okay. Then what do we mean by mechanical system? For those of you come from mechanical engineering school, then you should know, right? So mechanical system include three major items. Okay, mechanism, structure, appearance, right? And for motion provider, mechanism is more important. Structure, appearance is secondary, right? And inside mechanism, actually you only have two types of device. One is called the joint, another is called link, not mentioned here. So that means the structure which connect two joint together, we call it as link. So it's link is here. You see, link and the joint. It's very simple, right? Then for the joint, you have two types of joint. Okay. For those of you, you know physics, right? We only have two types of motion joint at the lowest level: linear motion, angular motion. Yes or no? 线性运动跟旋转运动. Right? These are the two basic motion, right? Then any motion is a combination of the linear motion, angular motion, yes. That's it, right? Then we just want to know, do we have a physical device which output linear motion? Answer is yes. We call it prismatic joint. Prismatic joint means is a physical device which only output linear motion. And this guy can move up and down. This is the linear motion. This is the prismatic joint, right? And then this one can rotate like our arm, rotate like this. This is angular motion. We have a pivotal joint, axial joint. It's just provide angular motion. So you see from the motion type point of view, very simple, right? So immediately you can link all these motion type with the physical device in mechanical engineering, right? Then you combine all these joint together, you build a robotic arm down the way. Okay, you can combine in a different way, then you have a different robotic arm. Then this video help you to understand how to design robotic arm, right? If you understand this video, good enough, right? So for this robotic arm, all the joints are the root joint. Okay, so each joint provides angular motion. So you see you have the fourth joint, fifth joint, and the last one is also another joint. The last one is to attach a tool. You see, the tool appears is to carry that robot hand. So the arm itself has a 6 joint. Then we say that this robotic arm has a 6 degree of freedom, right? And then you see control must come in. Okay? So you must have a motor to drive the joint to provide. And all the motion is programmable. Then you see, then you have a handheld device. You can say this is the iPad or handheld computer, right? So you can write the program. So then this video help you to understand mechanic system, control system, programming system are the 3 basic systems inside any robot, right? Okay. But you see this is another name, teach handler. This is a handheld robot. Okay, on top of the robot itself, then you can have a different type of hand, right, or tool. Okay, so that depends on the robotic parts. Okay. But so this video actually gives you an overview about the industrial robot. Okay, so it is very good. Then this slide summarizes what you've seen from the video. Okay, so this is a graphic representation about the type of joint. Okay, if you see the cylinder, means it's a joint which provides angular motion, right? So, but for linear motion, it is a rectangular box. Okay, so that is a linear motion. Okay, so you see, for linear motion, is this symbol. This is decay. That means you can move up and down. Okay, something like that. Then all this is angular motion, angular motion, angular motion, linear motion, angular motion. That's it, right? Here, okay. So it's very easier. And then inside each joint, we must provide energy or inject energy, right? So then we use a motor or actuator to convert, transform energy into motion. So if you have a four joint, like this, 4 motor. If you have 5 joint, 5 motor. All right, then all these link together. Now you see, when we study IoT, it's true that the robot itself is a typical example of IoT, mini version of IoT. Yes or no? Do you see this is IoT or not? This is the internet of actuator, internet of sensor. Yes or no? Right? So you see, when you study concept of IoT, you can apply here. Okay. So you see, this is a very magic combination of 3 major problems together. Actually, they help you to understand the detail of each individual problems. Okay, because they are all related. Okay, right? Okay. Then the third system should be programming system. But it is good to have a simulation module for your programming system, right? So this is the result made by our student. So this is done with the MATLAB. Okay. So besides programming language, try to have a simulation tool. But good news is when you use the MATLAB, it has a built-in, it's a same mechanism, right? So if you develop your own programming environment, try to offer simulation tool, right? So you see, here we simulate a robotic system. You pick up the object, place somewhere here. Okay, so this help you to know what is the programming system of the robot. Okay, so continue. So for any system, you remember this is 1, 2, 3, 4, right? 1 means one, when you can say 1 dynamic system or 1 motion system. 2 means 2 type of output, transient response, steady state response. 3 means 3 KPI, key performance indicator. All right. because robot is a system. Then how to evaluate performance? Same, right? 3, right? Is a stability, response time, response accuracy. 4 means what? There are 4 design methods for you to know. But we will study these 4 design methods in the second section when we study automation. Then you will know what is 4 design methods, right? Here, 1, 2, 3, 4. Okay, remember this 1, 2, 3, 4. Then you know what you have learned. Okay, so then 3 KPI is the same, you see, stability, response time, response accuracy. Then from here, you know, this actually this one you have, but this robot is stable, right? It's very fast, very accurate, right? So this help you to understand. Okay, once we achieve good value for these 3 KPI, then you will get the report like this, right? Yeah, okay. Okay, then we move on. Okay, then this highlight a little more detail about stability. For our manipulator, stability is not a big issue, it's very easy to achieve. But in case if you work, you design biped working robot, then this is an issue, right? Then you ask yourself, how come we can work stably? And what is the control system inside our brain, which control our biped working, right? You can ask this question, right? So this is the challenge for us to achieve, okay? And then this video is for you to know, right? How difficult for us to achieve very stable or human-like biped working. Now you see the big gap, right? Between this type of robot and Azimo. Azimo, they actually reach the stability, which is quite close to human like the stability of doing biped working. But for this type of robot, because of the low cost, then we will see stability is not so easy, right? I just made it in, then you see how difficult it is for us to achieve the stability for this type of low cost robot. Okay, good enough. So you see, it's not so easy to achieve stability, right? Then this is just a small exercise. I let you to verify because the answer is given to you, and then you just go through and do it a bit practice. You treat this as a homework, right? And this is another small exercise. So you treat it as a homework for you to go through because the answer has been given to you. And if anything wrong, then you let me know, right? And then for response time, this video give you an idea about the response time. So from this video, you will see this linear actuator could perform a motion in a very fast way, right? And we also named this robot as a 1 DOF robot. Okay, robot with 1 degree of freedom. Okay, this is a typical example of linear motion, right? So we just move along a single axis. Okay, this is another exercise. If you try to work out in detail, actually this is your warm-up you for you to study lecture 3, right? And motion, equation, etc. Okay, so let's say we draw this coordinate system. We will move for this. You can say this is the last link, right, to undertake the displacement of 20 cm, right? Maximum acceleration is imposed here, right? So then we want to know what is the shortest response time for this robot to achieve this requirement. Now pay attention now. Initially, the robot is at the rest. So after traveling 20 cm, robot must also at the rest. It's not overshoot or like that. So you must move, accelerate, decelerate, stop at the position of 20 cm. Okay, this is the scenario. Okay, so immediately you know this robot will make the two motion. One is acceleration, another is deceleration, right? So the shortest time means acceleration will travel 10 cm. Deceleration will also travel 10 cm, right? Then the both traveling time A together is a total traveling time. Okay, something like that. So then this is the velocity profile. Accelerate, okay, with okay, once you know velocity curve, the area underneath the velocity curve means what? This is travel distance. Okay, if you do integration of the velocity is what? Distance, yes or no? Integration of the velocity is distance, right? So that means this area corresponds to the travel distance, right? So this area must equal to 10 because these two areas are equivalent 20, right? So half time accelerate, another half time decelerate. Then immediately you know, okay, accelerate is a constant acceleration now. Maximum acceleration. Decelerate is the maximum deceleration. This is the quickest way to achieve the motion, right? So once you know this way, then immediately you can write down the equation of speed up motion is what? Motion with a constant acceleration. Then what is the travel distance? I guess this is year one physics, right? Initial position is 0. Displacement is equal to 1/2 AT squared. You remember this formula? Acceleration with the constant acceleration, travel distance is what? 1/2 AT squared, right? I guess you can remember this formula, right? Here. And the velocity, because it's a constant acceleration, velocity equal to initial velocity plus the increment of the velocity, A times C. I guess this is the year one physics, right? Here, okay. Then for slow down means you slow down at this position, right? That means you already z coordinate, you already travel here, z half of the time t, right? So then this is the increment during the deceleration. When you decelerate, your initial velocity is not 0. You have an initial velocity, right? So the displacement comes from two contributions. One is due to initial velocity times traveling time, right? Then this is due to deceleration. This is why we have a negative 1, okay? But the value, traveling distance is what? I can send 1/2 AT squared. T means the traveling time because your traveling time is only counted at this interval. Then it's a T minus capital T divided by 2, right? So you have this formula. And at this position, that means when T equal to half of the total traveling time, you can use this equation, right? Substitute T when the T equal to capital T divided by 2. Then you know this value, right? Then what is the velocity when T equal to T/2? Just replace the T by T/2. Then you know the initial velocity or slow down motion. This is the starting position of a slow down motion, initial velocity of a slow down motion. This is the boundary initial condition of this equation, right? Then based on these two equations, total travel distance should be equal to 20. That means when this T equal to capital T is 20 cm, right? So then you can solve for this capital T. When T equal to capital T, then this guy actually is equal to 20. Okay, I guess. Yeah. So this value is equal to 20 centimeter is 0.3 meter. Okay, so then you you get this equality, solve for t. It's very easy, right? So traveling time is one. Okay, so actually this is the year one physics. But you go through all this equation, this will help you to understand the philosophy behind the motion planning. So the lecture 3 will play on this concept. Okay, and accuracy is for you to know the error, right? And you will see for low cost robot, you will see how accurate it is motion is shaking, very, very shaky, right? Okay, so good enough. Okay, then accuracy means what? Accuracy means if let's say for this control, this joint has an error, this joint also has an error, then what will be the positional error of the two teeth, right? So this is a scenario. So now look at this question. So you have an error of 0.01 degree, error of 0.02 degree, then what should be the error which appear here, right? It's also in simple mathematics. So I help you to draw, okay, being like this. Okay, so you have a y coordinate, x coordinate, z coordinate, you have a V1, V2, joint angle 1, angular position 1, angular position 2, right? So then at the any configuration, only thing you need to pay attention is link 2 is mounted on link 1. Then this angle means relative orientation between link 2 and link 1. Then in order to write down the equation, we need to know what is the orientation of these two with respect to the global coordinate system. Answer is what? Answer is orientation, absolute orientation of a link 2 is equal to absolute orientation of a link 1 plus relative orientation of a link 2 with respect to link 1. That means orientation of link 2 with respect to the global coordinate system should be θ1 plus θ2. That's it, right? Because θ2 represents relative orientation of a link 2 with respect to link 1. That's it. You just need to pay attention to this done already. Okay. So, okay, absolute orientation of link 2 equal to θ1 plus θ2. Okay, done already. Okay. Then you can compute what should be the y coordinate if we know angle θ1 and the angle θ2. So you will see y coordinate means displacement along y-axis come from contribution due to the length of link 1 and the length of link 2. That's it. Because if you compute cosine θ1, then you have this distance, right? Then cosine θ1 plus θ2, then it's this distance. A them together is y4. Very simple, right? Okay, why I put the sine? This is the derivative. Okay, okay, this equation must come first. Okay, so that means y coordinate come from a contribution of the length L1, length L2, right? L1 times cosine θ1 is this length, right? Then L2 times cosine θ1 plus θ2 is this one. Then this one plus this one equal to y4, right? Then because we look at the error. What should be the error? First order derivatives, okay? Then, okay, derivative of cosine theta is equal to sine. Derivative of cosine theta is sine.
So is this EG101?
What? No, this is not.
It's here GR19 EG101
No, but this is the another training course.
What is this?
It's robotics automation. Right? Is it PR19? Which one? Oh no, because you know the TR. TR19 they will A in LHS. This is the NOS prime. Then go to there and sounds like NOS prime. It follows like me. If you do not put the LHS, then it's not prime. So then we just remove ET, then we can compute variation. How to get the from derivative equation get the variation equation? Then so this is the error, right? So then we consider worst case scenario. Worst case scenario means what? When this guy equal to 1, this guy equal to 1, then you have a maximum error, worst case scenario, right? So then you, let's say this equal to 1, this equal to 1, maximum value of the sine function is 1, right? So worst case scenario, then you put in the value, then you can compute. This is the accuracy of worst case scenario. Okay, what is the error? Okay, so this help you to know how to evaluate the accuracy of the count. Okay, simple exercise. Okay, so that's about the 3 KPI. Okay, then come to the guideline for you to follow in order to design robot as a product, right? So this is the general guideline. Okay, users need, then performance functionality of the robot, and then functionality of the robot, right? What are the needs of the user? Who are the user? What are the needs of the user? What are the functionality of the robot which could meet the need of the user? Okay. Then for each functionality, how to achieve the design? What should be the specification for you to come up with a design solution for each functionality, right? So then, based on the design specification, you do the conceptual design. Among all the possible conceptual design, you choose the best one, right? Then you follow the best one. You do the detailed design, embodiment design, select materials, select component, whatever. Build the prototype, optimize it until you obtain a very good prototype, then you go to mass production, right? So these are the basic thinking or flow for you to follow, okay, right? So, but here I just highlight the design aspect of 3 major systems inside robot. First is a mechanic system, right? So just like I mentioned, there are 3 considerations of when you design a mechanic system. One is a mechanism, second one structure, so one is appearance, right? For industrial robot, appearance is not important, right? But for service robot, then appearance is important, right? But for any robot, mechanism is very important, right? Without the mechanism, robot cannot move. Okay, so then second, important system inside the robot should be control system, right? But we will study control system is in the section about automation. So whatever we are going to learn from automation could be applied to the design of a robot. Now you see the relationship among these 3 major topics in this course. Okay. So when you consider control system, again, you need to pay attention to input, output, and inner relationship or inner process, which will produce output from the input, right? So, and the control device actually is for you to change the behavior of inner process. Okay, so then you pay attention. The input device should be sensor. Output device means what? Actuator, right? So we will study a sensor actuator in the third topics, which is about IoT. So you see all these 3 major topics are related to each other, right? Okay. Then for the design of a programming system, no one for us to reinvent the wheel. Good news is there are so many operating systems, no need to do the design, just use. There are so many researchers, software engineers, they are involved in this module, right? That is good news. There are many programming languages are there, no need to invent anything, just use them, right? Then you just use the library function to build up your own GUI, right? So maybe your focus is somewhere here. Use existing library function to design the user interface, right? No need to invent the programming language, no need to invent the operating system, right? So it's very easier. Okay. So that's about this second lecture. Okay. Maybe we take a break of 10 minutes, then we continue at 3:50, right? We take a short break and then okay, so we continue. By now, we have studied definition of a robot, the history of a robot, typical application with the use of a robot, and also we have studied the major guideline for you to design a robot as a product. So you understand that inside a robot, there must be three subsystems. First one is the mechanic system, second one is the control system, and the third one is the programming system, right? So roughly we should have this idea, right, about the robot, history of the robot, typical application of the robot, right? Mechanic system inside the robot, control system inside the robot, and programming system inside the robot, right? And from the definition of a robot, you know that the robot is a motion provider, right? And from the input output of the robot system, just now I mentioned, okay, strictly speaking, today's robot will only take the motion description as an input and produce motion as an output. Then you may want to know how come today's robot looks like that they are able to perform a task. So automatically you will know that the tasks are related to motion, right? Then there's an important topic which is about the motion planning. But motion planning is not very strong terminology, right? So we should call it as a task planning, right? Because the input to motion planning is a task. Why do we want to deploy robot in industry? The motivation is for us to use robot to implement or to perform a task. Okay, so and based on this title, immediately you know that many tasks actually could be decomposed into motion, right? So input should be task description, output should be motion equation, right? Keep this view in mind. Then you will see importance of this module. Okay, so lecture 2 is for us to know what are the major knowledge inside this module. And from here you see we do not discuss the way how to design robots brand. Good news to you is one, because today we have so many digital computer, just use digital computer, right? So this is why I only focus on the body, appearance, mechanism, structure, that is mechanism system of the robot. Okay, so these are the major topics for this module. But we will come back to the knowledge, study of the knowledge about the actuator sensor when we study IoT. So you see, okay, the third topics actually help you to understand what is actuator, what is sensor, right? Clear. Now we jump to this module. This module actually is for you to know relationship between AI and robotics, right? Because this guy take the task description as an input. Task description normally is in the form of human language. Then in future, robots should be able to read the text written in human language, right? So, but in today's situation, AI has not yet reached that level of intelligence. So this is why today human being must be there to help the robot to decompose the tasks all the way into motion description, right? Once you have a motion description, then today's robot is able to translate motion description into motion equation. Once you have a motion equation done already, then this module will be able to perform design the motion, right? But we will jump to this module when we study automation, because all the knowledge method that you are going to study in the section about automation can apply to this module, right? Okay, so now you see the relationship among these three topics. Okay, so for this section, we only focus on the last part of this module. But this module, strictly speaking, we can call it as man of the robot. So this is the man. This is the brain and the body, right? So you see, we separate man from the brain. For those of you who are interested in AI, you may start to ask this question: how come there are so many different viewpoints in AI? And the AI has a history of about 70 years. And how come there's no definite answer? There's no foundation or widely agreeable foundation on AI. Not like in robotics. Robotics we have solid topics, right? All these topics, okay. But in AI, we will see a lot of speculation. Okay, why is it so? Answer is what? This slide help you to understand, right? So, but it's very surprising. How many of you will believe that the man is part of the brain? How many of you will believe that the man is part of the brain? None of you? Oh, one. Okay. That means all of you, except this one, all of you believe that the mind is man, brain is brain, right? So then you are very smart, right? Okay. So when you are good, you should do research in AI, right? So the reason is what majority of the people or scientists has always a big guy. Oh, I want to take in computer science. They believe a mind is part of the brain. That is wrong, right? Okay, mind is mind, brain is brain. Okay, if you believe that the mind is mind, brain is brain, that means you are smarter than many researchers in AI. Okay, so this is the major reason, right? And then you know how come we also build up a foundation for AI. Okay, this is a very important departure. Okay, from doing all the AI and the new AI. Okay, yeah. Okay, so then we skip those human-assisted decomposition of a task into action into motion, right? We directly jump into translation of a motion description into equation of a motion. And in particular, we focus on the equation of a trajectory because the equation of the task is very, very simple, right? Pay attention to these two difference between these two terminology. I guess I will come back from a previous slide. You will see. Pay attention of trajectory. Trajectory means spatial constraint or spatial location with time constraint. Path means a spatial location without a time constraint, right? It's only with a time constraint that you can come up with equation, time equation of a motion. That could be the input to the control system, right? So why do we need to do motion planning? And this video help you to the answer. Because the robot can perform or control the motion, right? So all the motion is on the control of feedback control loop, right? So the input to the control system should be time function of equation. Okay, so without the time function of equation, we cannot achieve this, right? Here, so this is the motivation. Now you look at this slide here, you see you have a desired motion. All this must be time function of the motion. Okay, but for the study of a motion planning, you can describe a motion in task space, that's a physical space like X, Y, Z, or describe the motion in joint spaces like our, we have a lot of joint, okay, finger, okay. But actually, we not need to focus here because we have this mathematical equation to translate motion in task space into motion in joint space, right? So these are the theoretical study of motion. Okay, if you are interested in, then you read the textbook. This is the pure equation of the motion. Okay, not much philosophy behind, right? So, but it's just for you to know if you have a motion equation here, apply kinematic equation, you get a motion in joint space. Then this will be the desired input to the control system. That's it, right? Okay, so how to obtain all these time equation of motion? That is the focus of this lecture 3 in today's session. Okay, so then this is the last module or last part inside motion planning. Okay, or last phase, right? And the most important phase, right? Okay, so in between, you see, input to this one is output from task planning. What is the difference between two? Task means spatial location without a time constraint, right? Simple example is what is the equation of a straight line in two-dimensional space? What is the equation of a straight line in two-dimensional space? Answer is what? Ax plus by plus c equal to 0. Yes or no? Yes or no? Ax plus by plus c equal to 0. Yes or no? Next question. How to enable robot to draw a straight line? When you start there, yes or no? How do you enable a robot to draw a straight line? Why is it so difficult? Because you know equation of straight line, right? Then how do you enable a robot to draw a straight line? You see, so philosophy is very important. How means what? First, understand the philosophy. You need to aim time constraint. A robot can draw a straight line in 1 second, 2 seconds, 1 minute, 1 hour. Yes or no? You can draw slowly or very fast. Yes or no? But it's a different behavior. The straight line is always a straight line from A to B, not big deal. But you can go from A to B in 1 second, 10 seconds, or 1 minute or 1 hour. How to achieve all this kind of behavior. Now you see importance of trajectory. This guy is more important than fast. Yes or no? To write the equation of straight line, create ax plus by plus c equal to 0. Done. Right? How to draw a straight line from A to B in 10 seconds? You start there. Right? So they need to know, okay, how to enable a robot to draw a straight line with any specific duration. Okay, and the input from here is what? Is a motion description. Okay, straight line, circular line, or any curve, right? Polynomial equation of a degree 3, degree 4, degree 5, whatever, right? Okay, so once you know this, to write down the equation is not big deal. Primary school student know, right? Straight line, circle. What is the equation of circle? X squared plus y squared equal to r squared, right? Everyone know, right? Then how to draw a half circle in 10 seconds? Then you will start there. Yes or no? Okay. So then this one is more important. Here, okay. So what is the trajectory? So trajectory means you see, let's say this robot arm will move along the circular path from A to B within certain time duration. Now you look at its behavior. It will accelerate from A to C, then move with a constant angular acceleration or zero acceleration, a constant angular velocity from C to D, then decelerate from D to B, then stop at the point B, right? This is the behavior. Then from here, then you see, at least this robot will make the 1, 2, 3 movement So it's not just a single simple equation of a circle. Okay, so this will help you to understand the complexity of trajectory. Okay, just think okay the time constraint. This is very important, right? So spatial location, this could be positional location with a time constraint. That is trajectory. So this is more important, right? So you will see a lot of researchers when they write a book, they always write a paper, they always confuse between past and trajectory. You see, they just think that it's very simple. A circle is just a single equation. Actually, it's not true, right? Okay, must pay attention. Okay, so it's only with a time constraint then you can do these kinds of behavior. So all the behavior occur in real space, real time, right? Okay, so why trajectory is more important than past? The answer is what? Because for the control system, we need to have a time function of a desired motion. Okay, so this is why trajectory is more important. Okay, because it's through the performance of motion that give us the illusion about the performance of parts. Okay, so robot can only perform motion, right? But in future, AI comes in, robot can understand the description of parts. Then robot can handle everything. Just input task description, the robot know how to perform the parts. Okay, that will be the future scenario. Okay, yeah. So then what would be the equation of the trajectory of the linear motion? Look at the simple case about constant velocity. So you will see, but good news for you is okay. Complexity is what you need to have a time function for the spatial constraint. Good news is you can study time function of individual coordinate. Now you see, if you talk about the equation of a straight line, it's ax plus by plus c equal to 0, x, y mean together. Now you see, this is the independent time function for x coordinate, independent time function for y coordinate. Listen, right? So that is something good news to you. And here you see, this is the x coordinate as a function of a time. This is the polynomial equation of a degree 1. You can have a t squared, t cubed, or power 5 t, etc. Up to you, right? So you will see, actually, this is not a difficult question for you to answer. So if your way of thinking must change, right? Okay, so you will see, and you rewrite this equation of this form, then this is time function for x coordinate, time function for y coordinate, right? So this is a linear motion with a constant velocity. Vx, Vy are constant. Okay, and this is just a simple example exercise for you to go through. And I guess it's year 1 physics, right? But once you go through, you know the philosophy of the thinking is important. Once you adopt the right thinking, you know the requirement, then you can come up with a solution very easily. All right. Try not to confuse between paths and the trajectory, otherwise you get lost. Okay, yeah. So you treat this as a homework, like you go through, it's quite easier, right? Then what about the constant acceleration? Linear motion, again, linear motion, almost straight line from here to here, right? Now you see this also year 1 physics equation, right? So then displacement, you see time function of individual coordinate. Then you have a two contribution of the displacement. One is due to initial velocity, another is due to constant acceleration. I guess you remember 1/2 squared. Okay, this kind of things. For y coordinate, it's not big deal, right? Very easy. Okay, and this is also a small exercise for you to play and warm up, and you know, the thinking of philosophy behind the equation of the trajectory. Okay, time function of individual coordinate. That's it, right? Okay, so and the detailed solution is given here. I guess I let you to go through one by one step, then really you understand philosophy, because this is year 1 physics, very simple, right? Okay, then how about the variable acceleration? Previous case it was constant velocity, constant acceleration. How about the variable acceleration? This is also not big deal. You see, philosophy. Then we use polynomial equation of a time of a degree 3 of degree 2, degree 3, degree 4, degree 5, up to you, right? Okay, so degree 3, that means what acceleration is a function of time, right? Because if you compare second order derivatives, immediately you get the acceleration function or acceleration function inside you still have a t there, right? So acceleration is a function of time, right? Variable acceleration. That's it. Okay. So this is just a simple exercise for you to go through. Let me use a polynomial equation of order 3 or degree 3. You can compute the speed acceleration, right? Okay. So you see time is still here. You see acceleration is a function of time. So it's variable acceleration. Okay, very, very simple. Okay. And the previous case is about the linear motion. It's just help you to think about this philosophy of independently established equation of time for each individual, okay, x, y, z coordinate, right? So independent, but nothing prevents you for all these x, y, z. They still among them has a spatial constraint. That means they follow circular paths or linear paths or whatever, right? So that means implicitly the way when you impose initial condition for you to determine all these conditions ax, bx, cx, ay, by, cy. When you impose a constraint, this constraint actually will take into account of a spatial relationship among the x, y, z. That means all these x, y, z actually fall onto a circle or any curve, right? So this that means this you can put all this coefficient into the vector. Then all this vector has a little bit of relationship there. Okay, so this can help you to understand. Okay, at the end of the day, actually the time function actually has already considered spatial constraint, time constraint, maybe, right? And this will be the input to the control system, right? This will be the desired output from the control system. That's it, okay? So then you can also use a polynomial equation of degree 3, previous one degree 2, degree 5. Because when you have a more coefficient, then you are able to consider more complex curve. If your curve is very complex, zigzag or something like that, right? Then you must use a higher order degree of polynomial equation. Okay, so you just increase complexity of time function. That's it. You can handle because the more coefficient you have means what? You can have a more constraint. Once you have a more constraint, then you can have more spatial. More complicated spatial constraint, right? So this is a thinking. Okay, so that is a background knowledge. So you understand the philosophy for you to play with the equation of a trajectory, which is totally different from the equation of the path. Because for equation of the path, there's a straight line, circle, very simple, right? But once you jump into equation of a trajectory, philosophy is totally changed, right? And you need to consider time function of individual coordinate inside any position vector. Okay, so input. So actually, input to the trajectory planning include spatial constraint. Spatial constraint come from the equation of the path. The equation of path actually equation of line, equation of circle, whatever, right? So then you can use this equation to select key point. Here actually we just need to have some key point, okay, on the path. But implicitly pay attention, time constraint must be there. Also, another input is time constraint, right? So, and for spatial constraint, so these are the typical scenario of straight line, circular path, curve path. Curve path means any complicated curve, right? So these are the typical spatial constraint, right? Time constraint, okay, we always consider easiest case because when we talk about the planning, you must planning equal to design. Who is going to do the planning? Either robot or you, right? So this guy has the same meaning as a design. Then once you think in terms of a design, immediately you understand as a designer, you have the freedom to choose certain solution among all the possible solutions. But the guidelines are always choose the simplest solution, right? For time constraint, you see these are the simple solution. But don't make your life difficult. They say variable acceleration. You can't do so. You can't find a solution, right? As a designer. But why you make your life so difficult? Okay, easiest way is constant acceleration is zero with zero value, right? Constant acceleration is positive value. Constant acceleration is negative value, right? That's it. Okay, because you are the designer. Okay, if you think this way, then you enjoy your life. Otherwise, you make your life difficult, right? Okay, yeah. And once you have equation of motion, but remember, if let's say your role is to design robot as a product, then your robot must improve hardware and software. In particular, you must translate equation of the motion into library function. This will be part of your robot as a product. Okay, if let's say you are the manufacturer of the robot as a product, if you are the user or buyer of the robot, now you understand. You should not just buy a robot, then you use your eye to see, this is a physical product. Not good enough. You always remember, ask the vendor to show you what are the library functions for you to use. How easy for you to program this robot. Give you the jumbo program. Understand what I'm talking about? If you are going to buy a robot, this could be a very important criteria for you to choose the vendor. Why buy robot from this company? Why not buy from this company? Very important decisions are. Choose the robot which gives you very nice library function, very easy to use. Give you plenty example of a program. Then you feel comfortable, right? You just follow this example, you can make the robot move. If you buy a robot, there's no library function, no sample program. Then what are you going to do with this robot? You can do nothing, right? Because today's robot cannot speak Chinese. You cannot speak, talk to the robot, do this, right? Today we do not have such a robot yet, right? Okay, pay attention to this. If you are the buyer, must verify, okay, do you have library function? Understand? If you are the designer, if you are the manufacturer, must translate your equation of motion into all these library functions so that your robot could be easily sold in the market, right? Okay. So output of a trajectory planning. One, if you are the developer, then this is the output, right? Plus equation, it's very easier, right? But if you are the buyer, then you don't care, then you just need to know the vendor must sell you the library function. Okay, so at least equation of a mode trajectory and a library version of implement the version of this equation. Understand? Not just the equation, implement the version of this equation. Okay, yeah. So and then in terms of equation, what should be the typical representation of this motion equation? This is the general answer. You have a polynomial equation of degree 1, degree 2, degree 3, degree 5. Or for special case, if let's say you have a circular path, circle, equation of a circle, time function is about sine, cosine. But this is a special case, circular path, sine, cosine, right? And then translate all this equation into library function. Okay. And this is a far knowledge for you to know. Okay. At the beginning of the illustration, for a robot to draw a circle, you see three motion: speed up, cruise in, decelerate, right? So you have a three motion. You must make sure between two adjacent motion, there is a continuity of continuity, position, continuity, velocity, continuity, acceleration, right? So you want the robot to make a smooth motion so that you cannot see actually there are three motion here, right? If the robot keep this continuity, then you see very smooth, right? So this just really to know. Okay. So what do we mean by continuity in position? Means what? And that is for one motion at one particular time. Okay. Motion one position at this time must equal position at this time, right? So if let's say first motion is this equation, second motion is equation. At the same time, the junction at the T1, that means the X, Y, Z, both emotion are the same, right? Then you have the continuity. Otherwise, you will jump, okay? Then you will see the jump in the position, okay? And hopefully, the velocity is smooth. Otherwise, you move here, you stop, or you suddenly jump in acceleration, right? Then you continue the motion. Then no good jump, right? So it's not smooth, okay? As long as you maintain continuity in position, velocity, your eye cannot see any interruption, right? But always good to have acceleration. This is to increase, with this one, then you increase duration of the robot. Because when this guy is not continue, actually internally there's a jump in the force, but your eye cannot see them, right? Okay, but if there's an internal impact force, but it will affect the duration of the lifespan. Okay, this just for you to know. Okay, but if you want to simplify the cost, you just and this the two is minimum continuity position, continuity velocity. These are the minimum. Okay, if you are good, try to make acceleration to be convenient. Okay, and this is just a simple exercise for you to go through, right? And here you must be familiar with all this basic knowledge. When a robot 2D undergoes circular motion, then you see another terminology. V means what? Circular velocity. Omega means what? Angular velocity about the axis which passes through this one. When your 2D move around a circle, you just imagine you have the axis of rotation. So you have a circular velocity. This circular velocity, you just imagine has an angular velocity, right? So relationship is this one. R is a radian, right? And once you have angular velocity times c gives you angular position theta here. Okay, so these are the remind you about what you have learned in year 1 physics and mathematics. You need to know this, otherwise you will get lost of it, right? Okay, so xy could be two tips position. It's like this robot draw a circle which is parallel to xy plane. Then we only care about the xy coordinate. Z is constant, right? So something like that. So I just draw a top view. It's like this, right? Two tips move from A to C by following the circular path. Then you can just imagine I have this vector radian. He will rotate, right, from point A all the way to point B. Theta is the angular position of this vector, right? Initial position of theta is what? Pi. Okay, final position of theta is what? Negative pi, right? Initial when t equal to 0, initial position is 90 degrees, half of the pi. When t reach here, then this angle should be negative 90 degrees, negative pi over 2. Right? Okay. So circular velocity could be constant. It depends on your planning. You can see if a robot stay at the rest at the point A, it must accelerate, constant acceleration, zero acceleration, negative deceleration, right? Three motion or something. Okay. So then you will see equation of trajectory along the circular path. Okay. So if let's say you don't care about the start and the stop, this is the time function for xy coordination, right? Center of a circle, radian of a circle, cosine theta. Theta is this one, right? So once you let's say x0 plus cosine theta is x, right? Theta is this guy, then you substitute theta like this, right? Okay, so these are the time function of xy. In general, we do not consider acceleration, zero acceleration, negative acceleration. Okay, this is background knowledge we need to know, right? Okay, then, okay, based on this, immediately, let me see this guy continue move like this, okay? But later on, we will see how to achieve this behavior. Okay, the two teeth stop at this point, then move, then stop at this point, right? Move, then stop, right? Okay, but later on, we will see this is just let's say continuous move, okay, don't stop. Then this is good enough already, right? Then don't stop. Okay, you see, but what is the drawback of this solution? You need to have a library function for you to compute sine, cosine term, right? But some of you may say, today's computer all can implement this library function, okay? But it's true. You ask how much costs your computer? Quite expensive job, right? If let's say in future, if you want to come out a toy robot, right? Maybe it costs a few hundred $100, then you cannot afford to have a very powerful digital computer inside. In that case, if let's say your motion and you do not need to have an exact solution, then you can use polynomial equation to approximate circular paths. Okay, then you can avoid of using cosine sine function, because for low cost microcontroller, you do not have this library function. Understand what I'm talking about, right? So in case if let's say accuracy of the path is not, trajectory is not important, then you can use a polynomial equation, right, to make the computation easier. So this is an example. Let's say this robot base move from this location to this location along circular path, right? Then what is the equation of the trajectory? I guess for this one, you see, instead of using cosine, then we just treat this curve as a curve of second order, then use polynomial equation of the degree 2. You see, this is a time function of the degree 2 jump, right? To represent the spatial constraint instead of using cosine sine, right? So this is the any microcontroller can handle this a very cheap one, $1 microcontroller, right? Okay, so this is another way to to reduce the cost or reduce the requirement about the hardware, expensive hardware, right? So then when t equal to 0, they say my robot is here, cx equal to r, cy equal to 0, etc. Right? And then, okay, but you still know the exact equation of the trajectory, and you use this one to determine the wave one. That means when t equal to 1 second, I want my robot to pass through this wave one by following a curve, not circular path. Understand? So I use this exact equation to determine this wave one when t equal to 1, right? And you can determine another wave one when t equal to 2. You get the wave one. Because here you see how many coefficients are here. For each coordinate, you have 1, 2, 3. Use when t equal to 0, you can determine this two, right? You still need to have a two condition to determine ax, bx term. Then you can use this condition of when t equal to 1, where is this x? When t equal to 2, where is this x? Then you can compute ax, bx. Understand? Okay. If let's say you use polynomial equation of degree 3, then you have 3 extra coefficient here. Then you must use t equal to 1 or 1.5, t equal to 2, get the 3 condition. Understand? So this is the way for you to generate additional initial condition to determine ax, bx, right? Okay, second one. Done already, then it's good enough. So with these two set of initial conditions, you should be able to fully determine ax, bx, ay, by. Okay, this is the thinking. Then this solution can be implemented with any low-cost microcontroller. Then you can make your robot very, very cheap, right? then develop your robot as a toy, and then you sell it as a Christmas present, right? Clear? Okay. How do you use it to solve AX, EF, AY, BY? Let's see. This is the system of linear equation, write it in the matrix form, then compute inverse of this guy down, right? Quite straightforward. This is a square matrix. Then you see inverse of this one times this one down. Okay, clear? So this is a way for you to achieve a cheap solution. Okay. So the previous slide showing you the background knowledge for you to use, right? Then in actual application, then you follow all these guidelines, right? Just now I already mentioned, if you are the seller or manufacturer of the robot, you must do something extra, okay? And translate equation into the library function, and eventually you have a GUI, and then so that they use buyer of the robot and GUI, right? And if you are the buyer, make sure the designer of the robot bought by you has already built in all this library function. I'll sell you, give you the library function, right? So that means if as a user you can use the library function to program the robot, or if the buyer or seller give you a GUI, then you use GUI to do the programming of the right? So it's up to you. Okay. So and okay, this is a short video, okay. So from okay, this could be a scenario as a buyer. So you see, you must as a seller of this robot, you must provide okay all these library function for the buyer of the robot to use, right? So you see, we stop this some extra function are not so important. I guess only one important is a move, right? Okay, you see, when we call then there's a function detect the distance we will stop, right? So this just help you to know as a seller or manufacturer, it's good to build up all these library function and develop. This is GUI from you offer the GUI, allow the user to easily buyer to program your robot. Okay, this help you to know the requirement as a seller of a robot, and also help you to understand the requirement from the buyer. So buyer will like to do this kind of activity, just call the library function provided by you. And this is about the sensor, right? Okay, know the distance sensor. Solar means the distance sensor, right? Okay. So just now you see the video. So it is basically it is a result of running this program. Okay. Now you see this kind of behavior. But then you want to know what is inside this function, right? So inside this function, you see you have a lot of code. I guess this should be good enough. Then it's telling you more. But it's cooler. So you know, okay, as a vendor or seller or manufacturer of a robot, you must translate equation of the category into a library function so that the user buyer just use your library function to do programming, right? And another thing is it is always good to provide this GUI. This is the GUI, graphic user interface, allow the user to program, to design the trajectory, right? So I just created the video, right? So you see, you have a virtual interface, and this area for you to write a program. And then here, by pressing all this button, you should be able to write a very short program. Okay, and then here is for you to visualize the virtual workspace of your robot. You can consider this is a virtual workspace of your robot. I guess today you may have heard of this terminology of a digital twin in Java. This is what? This is the digital twin of real robotic arm, right? Okay, so that means in future, as a manufacturer, you must have a real robot plus a digital twin of your robot. Then you can fulfill this scenario. Then user can use this UI to program a digital twin. If the digital twin of your robot arm perform correctly, then you send the program into the real robot down the line. Right? This just give you an idea about why do we need to know equation of a trajectory. It is to support the implementation of a library function plus GUI like this, and also the digital twin of robot. Understand? Okay, so that should be good enough. And then we want to know how to translate all this background knowledge into actual design of a trajectory. This is more guideline for you to come out this. You see, speed up, zero acceleration, slow down. Okay, so you will see typical scenario is motion with a 3 phase, right? Speed up phase, cruising phase, slow down phase. This is the typical scenario. Eventually, you may skip up the middle one. Speed up, immediately slow down. Then you have a fast response, right? Okay, and then for speed up trajectory, this phase, speed up phase, you can have 3 options: either linear path trajectory or linear path trajectory or curved path. You see, path is not equal to trajectory. You can talk about trajectory of the curved path. This guy imposes a spatial constraint. Then you see with a time constraint. The both A together is trajectory, right? Something like that. Okay. Then for the second phase, the cruising phase, you have 4 options, right? Linear path, linear path, linear path, middle is the constant speed, constant acceleration, variable, etc. Specific time constraint, etc. Then third phase, the slow down phase, again 3 options, right? Then actual design, you can design a trajectory with only 2 phases or 2 paths, 2 phases, right? Speed up, slow down. Then immediately you know that you have all these options, right? Because for first phase, you only have 4 choices. This guy 4 choices. When you combine them together, eventually you have this combination, right? If you have a 3 phase for your trajectory, speed up phase, cruising phase, slow down phase, then this is an A combination. That means you only have an A design solution, right? You choose anyone up to you, right? Then this is the illustration that help you to understand what we mean by, okay, first phase is the linear path, second phase is linear path, so something like that, right? From A to C accelerate, C to B accelerate, down, right? Also, they belong to the same straight line, okay? But internally, you must think this trajectory consists of 2 phases, right? What do we mean by linear path for phase 1, curved path for phase 2? You can see, looks like this, right? What do we mean by curved path for phase 1, linear path for phase 2? Then is this illustration. Okay, this is to help you to understand what do we mean by first phase with the curved path, second phase with the also curved path. Then see here, AB is a curve, CB is a curve. That's it, right? Yeah. Okay. Then this is an exercise for you to play with this concept, and then you will feel confident. Okay. Mathematics behind is very simple. Philosophy is very important. All right. So this is real case. You see, we may have a very big robot like this to print a house from, okay, layer by layer. Then at one particular time, if let's say we want to print from A to B, right? And then A coordinates are 10, 50, Z is 3, B is 2, 5, and 30, right? Go from A to B, then we draw coordinate system like this, right? Initial position A, final position B. Then constraints are must finish this printing in 12 seconds. Look at the question. Now you see time constraint, 12 seconds. Then come out the solution for robot to achieve this task. But now you see, okay, this is a design question. But try not to put yourself as a student. Student always like you need answer them. How many solutions for this question? Answer is what? Infinity number of solutions. Then you get lost. You think network solution means no solution because I do not know which one to choose. Right? If you think in that way, then it's wrong. You must put yourself into the mindset of a designer. You see, design means what? That is advantage. If you have a lot of solutions to choose, then you take your free, enjoy your freedom to choose anyone. Understand? Okay. So then you see, this is just guideline for you to enjoy your freedom as a designer in choosing any solution. Okay. So, but as long as your solutions fulfill the requirement, these are the requirements imposed by the task, right? Finish the printing in 12 seconds. Must go from A to B. Then travel distance is what? Once you reach B, y x coordinate is 2. And the A x coordinate is 10. 2 minus 10 means what? Negative 8 meter, right? This is travel distance, right? This is imposed by the task genre. The rest you enjoy the life of it, right? Okay, then you say I'm a designer. I choose the 3 phase for this category and a speed up phase, cruising phase, a slow down phase, right? Then you enjoy your freedom as a designer. Then you say speed up phase take 2 seconds. You can say 2.1 seconds up to you, or 2.11 seconds up to you, right? This is why you see you have an infinite number of solutions. You can say 2.0, 2.1, 2.11 to you, infinite numbers, right? Then cruising phase 8 seconds, slow down phase 2 seconds, done already, right? And some of you may say, why not the 1? It's up to you, it's okay. You say 1, then it's 10 now. 1, 10, 1, 2, 8, 2, up to you, right? Okay, once you decide, make this decision, the profile of velocity is on already. From 0 to 2 seconds, constant acceleration. Between 2 to 10, 0 acceleration. 10 to 12, negative acceleration. Okay, this we call velocity function of x coordinate. Already, right? Then, what is the equation position time function for x coordinate in this phase? Right? Very simple, constant acceleration, then 1 over 2 squared. Then what is the time function for x coordinate in this phase? Because this is a constant velocity now. What is velocity at this one? When t equal to 2, then 2a is 2a times time duration. What is the velocity at this one? Same of the constant velocity. What is this motion? Negative acceleration, constant negative acceleration, right? So negative 1 over 2 at squared. Very simple, you see. Okay. Then what is the total travel distance? That means what is the total area underneath the velocity function? Answer is what? A. You remember? This is imposed by this travel distance is A, right? Yeah. So then you determine what is the travel distance. Once you reach here, you add all these 3 together, right? So then when t equal to 2, then you have this equal to d. When t equal to 10, this equal to d. T equal to 12, this equal to d. Add them together, you see this cancels out. This cancels out. You only have this equal to this. This is what. This guy equal to what? A meter, right? Then A them together, A meter. Then immediately you know what should be the A. Done already, you see? Okay. So once you know A, all the time function for each phase are done already, John. You know every step. This will be the input to the control system. You activate the control, then robot do the built-in finish. Yeah, right? Okay. So you go through, okay, you still treat this as a homework. You go through, digest this exercise, then you enjoy, right? The motion planning and the topics. Actually, philosophy is very important. Mathematics is extremely simple, right? Okay. If you do not know the philosophy, then you lost it. Okay. Then how about circular motion? It's similar. Previous ones are linear motion, 3 phase. Circular motion at the beginning, I also mentioned 3 phase from A, C, C, D, 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 right? And I draw the top view. This is the top view here. Let everyone understand. We do not care about the Z. Z is a constant. only take care of x, y. This is top view, right? The robot will move its hand from here to here. Then you see this is y, or y is here. This is point A is here, B is here, point B, right? Top view. Okay, now focus on this one is easier, right? So then you see duration is 12 seconds. Center of the circle is equals to u. Radius of circle 15, right? I guess it's the constant circular velocity. Oh no, it's planned by you. Okay, acceleration, cruising, deceleration. You just define this vector initial position. This vector point to point B. After the full rotation, this vector will point to point B, right? And then this vector will stop at the point B. Start from point A. Just imagine you have a vector rotate about the axis which pass through point C. Let's say, let this help you to understand you have an angular position theta t, right? That's it. Okay. So based on that, this is as a designer, I would say you choose say this motion will include three phases: speed up, cruising, slow down. Allocate time, speed up take 2 seconds. Cruising 8 seconds, slow down 2 seconds, right? And then this is the background knowledge, right? So you have we call circular acceleration or tangential acceleration. Pay attention, a circular acceleration, then you have an angular acceleration, right? So it's like a circular velocity, angular velocity. Try not to confuse this group, right? So if you have a tangential or circular acceleration, that angular acceleration equal to circular acceleration divided by radian. Radian of a circle. Radian is this vector, its length of this vector. This is radian. That's it, right? If you know this, then it's enough. Here I'm going to show you both solution, exact solution with the equation of a circle. This is an approximate solution with the equation of any older curve line, right? In case if you do not have a powerful microcontroller to handle computation of sine, cosine function. Okay, this is the approximate solution. This is the exact solution, right? So this is the same as the previous slide. Equation of circle is what? X minus center of x coordinate equal to the radian times cosine theta t. Cosine theta t, you know, pi 90 degree minus 1 over 2 squared. Because the first phase is what? Constant acceleration, right? So accelerate 1 over 2 angular acceleration times t squared, very simple, right? So then you plug in substitute this guy because duration is a t 0 to 2 seconds. When t go to 0 and the t go to 1, you get the intermediate condition. When t go to 2, then it is a final condition, right? So you get this. You can use all these conditions to determine AX, EX, CX for approximate solution. But for exact solution, done already is this one. Okay, yeah. Then for second phase, from time t 2 seconds to 10 seconds, exact solution again is the same, right? Only difference is equation of theta. Because for second phase, theta is will increment due to initial velocity because there is no acceleration. So theta t will increment, okay, increase due to initial velocity omega 2, right? That's it, right? So this is the exact solution, but you still can create a three condition for you to solve this three condition. They say that the t equal to 2, t equal to 6, t equal to 10. You get the three condition. This three condition good enough for you to solve these three condition. It is approximate equation, right? Remember, below is exact solution, on top is approximate solution. That's it. Okay. Phase 3, slow down is a constant acceleration, right? T equal to 10 to 12 seconds. Then only thing is theta t will be different, right? Theta t will increment due to initial velocity plus initial velocity. Here I put the plus because alpha itself is negative, so it's up to you, right? So either you put treat alpha is positive, then you have a negative here, right? Okay, it's up to you. Okay. So then this is the exact solution. Based on exact solution, you come out the three conditions. When t equal to 10, 11, 12, use these three values to help you to determine these three coefficients inside the approximate solution. That's it. So this is for x coordinate. Then you repeat for y coordinate is exact same procedure, right? So exact same procedure. So I let you to go through, then try to fully understand. If there's any issue, let me know, right? Okay. So that is okay. The way how to translate or determine an equation of a trajectory, then translate an equation of trajectory into likely function. Okay. Then you may want to know, okay, can we automate the previous procedure? And without the human intervention, let the robot do all these things. Are we able to do that? The answer is yes, right? So you need to have a sensor. It's like a robot try to, without the human intervention, just tell the robot to perform a specific type of motion. That means that you just tell the robot motion description. Let the robot to come out the equation, translate into likely function. Are we able, our research has reached this level or not? The answer is yes, right? Okay, so I'll show you one more. This is what we have done. This is a demonstration in year 2008. Okay, you see have time. 2008 is 15 years ago. So you see, this is a fully autonomous behavior. There's no human intervention at all, right? So the robot uses binocular vision, look at this object placed in front of it. So he autonomously determine XYZ coordinate, use this knowledge to plan the motion of the arm plus the motion of the finger. But pay attention. The knowledge perceived by the vision system is a geometric description with respect to the coordinate system assigned to the vision system. Immediately you understand now. Robotic arm has a coordinate system, vision system has a coordinate system, hand has a coordinate system. So internally, he will handle all this transformation, right? And then plan the motion of arm, plan the motion of finger, etc. Right? So this just help you to know that more than 10 years ago, research has already reached this level, which will enable today's robot to autonomously undertake trajectory planning. That is good news to you, right? But since this is not so popular, but as a design engineer, you still need to know all this knowledge in case if you work as a design engineer in a company which will design robot as a product, at least you know how to come out equation of trajectory and translate equation of trajectory into likely function. Okay, so this just give you knowledge or research, okay, or advanced research, which has already reached the level which will enable today's robot to autonomously plan the trajectory. This is another example. I guess I've already shown you. Okay, even for this car to follow the moving target, there's no intervention of human being. So all the motion, that means linear motion, angular motion. Pay attention to the wheel. The wheel has a steering wheel, right? So all fully determined by the vehicle itself. There's no human intervention, right? Okay, so you pay attention to this. So there's a linear motion, angular motion, right? Okay. But this video is quite long. Okay, I just show you a solution. Now, this is an iterative solution which will enable car-like vehicle to plan. You see, because for car-like vehicle, the two coordinate will be angular position of a steering and the linear velocity of driving. So for a car-like vehicle, we have only two coordinates, right? Generalized coordinate. One is driving velocity, another is what? Steering, angular position of the steering. Then you see this is the function for vehicle to generate. But this function will take the distance between our vehicle and the target. Inside the target, you just need to know which one going on. Right? Okay. So this just need to know. Okay, that ends today's study. Okay. So we only have 6 minutes left. So we just do a short Q&A. Okay. So we have spent 3 hours to study robotics. Okay. So quick summary is what? Now you know what is robot, yes or no? Right? You know the history of robot, and you know that shuttle puppet should be considered as the first generation of a teleoperated robot. Right? Okay. And then you know robots can do a lot of things in industry. Okay. So and then you know how to design a robot as a product. Inside the robot, you have a mechanic system, control system, programming system, right? Okay. So, and then in order to make your robot to be programmable, always remember you need to have an equation of a trajectory. You need to translate equation of a trajectory into likely function, right? Okay. Before you can sell your robot as a product. So the last lecture is for you to know, okay, why today's robot is programmable. You know the answer, right? We have a likely function. Okay. So our last message for you to know is today we are able to let the robot to autonomously determine desired trajectory, okay, based on the sensory input. So in future, okay, at the motion planning level, at the trajectory planning level, we can let the robot do the task. Okay, yeah. Okay, then any question or Q&A or you want to ask? Any question? You can still singular. If you have a question, then tomorrow we have a second session and you can still ask, right? Okay. And tonight go back now, you read through the lecture slide for all the example, you treat them as a homework, but also solution on inside. You go through, then you will yes. Okay. So at least you remember what you have learned from today's section. Then in future, if people ask you what is robot, what is robotics, right? What are the major issues in robotics, you should be able to answer. Right? Yeah. Okay. Question? No. Okay. Thank you for your attention. I see you tomorrow.